everybody for coming to this workshop. It's really nice to be here in Cambridge. So this talk dates back to my PhD thesis, so it's very much joint work with Michael Weinstein and Mark Spiegelman of Columbia. And it can be seen as a case study, it can be seen as a case study in applying the sorts of methods that Greg talked about yesterday and today towards the problem of partial melts. So we'll see how far that approach takes us, what it can do, what it can't do. So I'll go through the physical motivation. I'll make some comments on the history of these models for partial melts, and then I'll go through our work and some things that I hope happen in the future. So just for the people who aren't the geophysicists, the goal here is to say something about why the Earth looks the way it does. Why do we have plates? Why do the plates move? Why do we have the distribution of plates? So you have all these different things going on. You have solid state convection in the mantle, and up here at the crust we have linear elastic brittle mechanics. If we look at the distribution of plate boundaries, we see very strong correlations between where we have plate boundaries, where we have earthquakes, and where we have volcanism. So those are going to be the most interesting things to model, to figure out why we have these interactions. And this comes into the question of partial melts, because what else is frequently present there is partially molten rock. And what I mean by that is that we have our convective process in the mantle. So rock is coming up to solidus, it's coming up mechanically. At some point, it crosses a solidus line for one of the constituent minerals, and that mineral melts out. So what we have here is these are these synthetic rocks from Warwick and Watson. But the idea is that we bring the rock up under mechanical forces, and then thermodynamics comes into play, and some of the constituent minerals melt out. And we end up with this matrix of grains and melt channels and pores. And the big challenge, which people have sort of alluded to in the previous talks, is getting melt to the surface fast enough, or the mechanism by which melt travels to the surface fast enough to explain observations of the sort that have been talked about with regards to the radioactive isotopes. Because you actually have to get things up pretty fast. And then we have, so there's this belief in this porous flow mechanism and the focusing, and these are talks that we've seen these figures before. So those are the Dunites of Oman, and that's the Dunite channel, and that's the Hartsburgite around it. So this has now been depleted in the pyroxenes. And we also see mechanical localization from Ben Holtzman and Dave Kolstedt's lab, where they had localization of the melt into these bands. So there's all kinds of nonlinear pattern formation going on. So what I'll call the classical common assumptions to the models for partially molten rock are that at the grain scale, so we go down to the millimeter scale, or possibly smaller if you're looking at the laboratory scales, and you're imagining that you have two fully interpenetrating fluids. They're effectively incompressible, and they're viscous. We're zero Reynolds number, so our primitive equations are going to be the Stokes equations. But some of the things that we want to see is macroscopically we want to see that there's this effective compressibility of the grain matrix. We should be able to squeeze the grain matrix and expel fluid from the pore channels. We should be able to dilate it and suck fluid in, which is a property that is not found at the grain scale. The grains are effectively incompressible, but we're going to see an effective property that emerges, which is compressible behavior. And it's in the same spirit as how at the grain scale, if I go down to the pore scale, there's no permeability in the pore. The permeability is a macroscopic effective property that emerges. The other thing that goes on here is we have a very high viscosity contrast. 20 orders of magnitude viscosity contrast between the melt and the matrix. So the historical developments, okay, so the earliest sort of fully fleshed out models date to McKenzie and Scott and Stevenson, and they were based on ideas from multi-phase flow. At sort of around the same time, you had Fowler, who developed some thermodynamic models, And there have been refinements since then. So there was these refinements by Spiegelman and Katz and Takai and Katz more recently with viscous anisotropy. And at the same time, in around 15 years ago, Berkovici and his collaborators, like Zosh, they started to look at using really systematic multi-phase flow techniques based on stuff you'd see in Drew and Passman's textbook to get effective equations, and they added in a lot of new physics in the process. But all of these sort of begin at effectively a macro scale with their models. And what I really wanted to get at with this work was to try to figure out what a basic grain scale model was that could be systematically coarsened into effective macroscopic equations. And I wanted to get something else, which was the bulk viscosity. So these are equations which are the sorts of things that you'll see in the PDE models. So there are the time dynamics, which are conservation of mass and momentum. I'm not going to talk about these. The left-hand side makes a lot of sense. That's the conservation of mass. The right-hand side is thermodynamics. I'm not going to touch thermodynamics. There's a Darcy's law, which we've talked extensively about. And then there's a matrix force balance equation, which relates the velocity, the strain rate of, and the velocity field of the matrix, coupling it through the fluid pressure here, which then in turn couples to Darcy's law. And in fact, that's something that we're going to see, that the real coupling between the matrix and the melt happens through the fluid pressure. What else do I have to say? Yeah, and there we go. There's a bulk viscosity term, which is not found at the micro scale. The other thing that shows up is that even if you can argue these equations out, is what do these constitutive relations look like? So the permeability, we believe, is something like phi to the n. The bulk viscosity, historically, and in this work, looks like maybe phi to a negative power, although, as we've seen in talks by David and Yasuko, it's probably something else. And this talk will reveal what's probably wrong that needs to be fixed in order to reconcile the theory with the laboratory observations. And of course, there's chemistry and physics. So the real motivation for this work in many ways was the following, was I had some competing research at the time in which I found that if I had a bulk viscosity that was like 1 over phi, I could prove quite a bit of, in terms of well-posedness of a PDE. So I desperately wanted to have a justification for a 1 over phi bulk viscosity. And I also did want to come up with a full systematic formulation that would lead to these kinds of equations from a grain scale model. So those were the objectives. Figure out what the bulk viscosity is and why it's there, and get to equations that look like this from a primitive model. And these slides are out of date, obviously, because Rich has done quite a bit since then, but people have used these large-scale PDE models to make predictions that have some amount of agreement with lab and field observations. Okay, homogenization. So the challenges here is, can we get to the macro scale from a micro scale or a grain scale model? And can we say something about what the constitutive relations are? So there are a couple caveats here. Our effective equations reflect our grain scale assumptions. If the macro equations are then inconsistent with the field and lab, it says our grain scale model is wrong. And in fact, that's what I think in some ways, in light of the other talks in this workshop, that's the takeaway. So one of the assumptions that goes into this is that we're going to treat the matrix as an isotropic Newtonian fluid. Prediction of this model is that if it's an isotropic Newtonian fluid, it's going to have a 1 over phi bulk viscosity. The experiments say it's not 1 over phi. The conclusion is the matrix is not an isotropic Newtonian fluid, or at least it can't be modeled as such, at least not if we want to have something that agrees with the lab. The other caveat, and this comes back to the constitutive relations, and it also is touched on in the talks that Greg has given, is when it comes to the effective parameters, you may need to compute. So there's simple 1D cases where the effective parameter might be a harmonic mean. In general, it's imposed in terms of solving a PDE. If you really want to know what this value is, you have to solve the PDE, and you have to do it numerically, because you're interested in problems in 2D and 3D. So the main results, just to summarize, so this appeared a while ago back in JGR, is we can get equations that look a lot like the equations that appear in McKenzie's 84 paper by starting with two viscous fluids at the grain scale via the techniques of multi-scale expansion that you see in homogenization. And in a self-consistent way, we can get these parameters out, that the permeability is like phi to a power that we found to be a little bit bigger than 2. And that very much reflects the choice of our grain scale domains. I fully expect that if we used more realistic domains, we'd get a power that was consistent with what Wen-Lu got. We got a bulk viscosity which looked like 1/5. So again, here's the inconsistency. Let's see, did I put that on there? Yeah. So as David has mentioned, the ratio should be 2. Here, the ratio is going to be like 1/5. So this is sort of one of the takeaways in light of this subsequent research, that the isotropic Newtonian model for the matrix is not adequate. So we'll see where this comes from.
We can talk more about why the bulk viscosity is insensitive to microstructure.
I have
that's incorrect.
Well, that's incorrect. That's incorrect in light. It's incorrect if you go to the grain boundary diffusion model for deformation. For the fluid mechanical model, I think this is correct. We'll see. So again, just a little bit of a recap on what Greg has talked about. What happens in homogenization? You have a domain, this shaded region. You have a microstructure within the domain. And there's some length scale relating the grain scale, which is a little l, to some macroscopic length scale that's capital L, and that gives us, the ratio gives us epsilon. So we have to start with a PDE that we believe is correct if we had unlimited computational resources. So here what I'm writing this as is L epsilon, U epsilon. So this is some linear piece of a PDE model, and this might be some nonlinear piece, and then we've got a forcing term. And we need this separation of scales to be present. So as we've seen, what do? We take our field variables, whatever they are. We do this 2-scale expansion, or as is possible, you can even have more than 2 scales. You could have a Q-scale expansion, but it's a perturbative solution. And throughout this talk, we're assuming that we're periodic. We're assuming the microstructure is periodic. So in the fast scale, all of our field variables are going to be periodic. I hope that by the time Claude finishes lectures tomorrow and on Friday, we'll have a sense of how to generalize this, at least to the case of a random media, which might be a more realistic model than a periodic media. So when we do this, all of our derivatives that are going to appear in here are going to get mapped like this. So it was just a derivative in x. It's now a derivative in x plus 1/epsilon, the derivative in y. So just as a 1D example of this, what Greg talked about, here's a little 1D plus-on problem where I've put a periodic diffusion coefficient here. So it's 1 plus 0.9 cosine 2 pi y. So it's period 1. And I've computed a variety. So we'll do the multiple scale expansion. The leading order piece will turn out to be independent of the fast scale, and it will solve this constant coefficient one. So for this value of a of y, the effective value is about 0.436. And that's the harmonic mean of a. So it's 1 over the integral of 1 over a. So if we look at the computed solution here, this light blue one here you can see is fairly smooth, but you can see on the blue one you see the signature of the microstructure. And then you see as we reduce that, we have the green one. That still has some of the signature. It's also more oscillatory. And the red one is closer to blue, and that's also more oscillatory than the preceding ones. So the blue one there, that light blue one, that's the solution to this, which is just a quadratic. And I also included this purple one. The purple one is what you would get if you computed this with the simple average of A. The simple average of A in this case is 1. So again, not to beat a dead horse, but the effective equations are not necessarily the simple averages of the microscale ones. At the same time, I do want to add one addendum to that. Sometimes they are. So it may not be of interest to people here, but in optics, people are very often interested in Schrodinger equations or Schrodinger operators with potentials that are periodic. So they have optical fibers, and they'll have a potential that may have some slow variation, but it'll have some fast periodic variation. And they might be doing things like looking for bound states of this, so they'll have some E of psi on there for the eigenvalue. And in certain cases, the leading order homogenized equation here is absolutely the simple average in the fast variable. So this is not a case of black and white, that sometimes it is the simple average and sometimes it isn't. You really have to work through the problem to see which case you're in. Another comment which I want to make about this figure is, in a pointwise sense, it looks pretty good, in that the oscillatory curves are getting closer to the smooth cyan curve as epsilon gets small. But if you think about the derivatives, you're in big trouble. So what I have not included in this figure is the so-called corrector, which is this first correction, the epsilon u1. And as we saw in Greg's talk, there's a way to compute that. If you're interested in a problem where you need to get the derivative right and not just the function, it is essential to include those correctors. And the way to see that is what happens when we take a derivative of this in x. Well, this guy turns out to be independent of the fast variable, so we just get a u over u0x. When the derivative hits this one, we get an epsilon, but then in one of the arguments we get a 1 over epsilon. So that makes an order 1 contribution. So there, again, it may not be relevant to what you're after. There are going to be problems where you may need to know that you're not just getting the function right, you're also getting the derivative of the function right, in which case it's not just about solving the effective equation. You actually have to go back and put the correction in. So this is our primitive model. Coupled isotropic Newtonian fluids in a periodic medium. So I'll use the superscript S for the solid, which is, say, the matrix, the superscript F for the melt, the fluid. And at the interface, we're going to have continuity of normal stress and continuity of velocities. So these are, of course, these 2D cartoons that I draw just to indicate that these are periodic. This is not a connected network. Please keep in mind that while I draw these cartoons, I really mean that these are topologically connected. It's doubly connected networks. And just notation, of course, so omega is the cell. We partition that into the fluid region and the solid region. The volume of the fluid region is normalized to be exactly the porosity. The volume of the solid region is 1 minus phi. There's an interface between the fluid region and the solid region. That's gamma. There's the other part of the boundary. So there are two pieces of the boundary of both omega f and omega s. There's the piece that's the interface, and then there's the piece that's the periodic piece of the unit cell. So when I refer to gamma, I'm really talking about the fluid-solid interface, but there is this other piece to the boundary, which is the edge of this computational domain. So there are a couple of weaknesses here that I want to point out, which of course is that, for starters, the matrix is not isotropic. The matrix may not even have what I would call a local rheology. So by local rheology, I mean it's some function of the strain rate in the sense that it's the double contraction of the strain rate to some power against the strain rate. It may be something like that's been alluded to, like in grain boundary diffusion, where you may actually have to solve for chemical potential in order to back out the relationship between stress and the strain rate. This periodicity is very strong. These are not periodic materials. They might be locally periodic materials, but they're not periodic materials. And even if by some miracle we could set the problem up so that it initially is periodic, the grain things are going to move. And when they move, you're going to break periodicity. So that's something else that actually I think is quite interesting. And that's this problem is present in a lot of these multi-scale problems where you're not just, it's not, so homogenization, when people started doing it, they were really thinking of things like aircraft composites or ceramics. And in those cases, you fabricate the material. You might have some defects in the material, but basically it would be, for instance, a layered material, and it had its properties and it would wear out over time, but it was reasonable to assume it was a static microstructure. In these problems, the microstructure is not static by any means. It's going to evolve. And I think at least an outstanding, I'll suggest on how we can deal with this, but at least a mathematical challenge is to figure out how you could systematically couple microstructure motion to the macro scale. It's also purely mechanical. There's no thermodynamics in this model, which is part of why I said there was no melting. Okay, so this is a big deal, this non-dimensionalization issue. And in fact, for a long time, I wasn't making any progress on this problem because I didn't have the scalings right. So scalings are essential to getting most of these homogenization problems right, and we'll see how that shows up. But if we didn't have the scalings right, we wouldn't get anything out of this, or we wouldn't get anything meaningful out of this. So I'll use capital letters for my scaling parameters with the exception of the length scale, little l. So after non-dimensionalizing the two force equations, we have four dimensionless numbers. And I'm also including buoyancy here, in addition. So we have this term here, which is the ratio of forces, of pressure gradients versus viscous forces. And we have this term here, which is the ratio of pressure gradient to gravitational forces. Three more numbers that are important are the characteristic velocity ratios, the viscosity ratios, and the pressure ratios. And we want to eventually express this in terms of epsilons. So I want to get rid of all these dimensionless numbers, these different dimensionless numbers, and just have epsilons in the equations. And everything else is dimensionless. So we need more assumptions here. So what we can begin to do is say, okay, I went back and when I non-dimensionalized this, I non-dimensionalized it to the fast scale, the y variable. There was no reason I had to do that. I could have gone back and non-dimensionalized it to x. So this is little x with not capital X. So the capital X for me has a scale, has a length parameter associated with meters or kilometers. My little x is still the macro scale, but he's dimensionless. But I could have done that. And we expect at the macro scale that QL and RL, everything sort of balances in these equations. So these can all be order 1. But then when we work with that, well, QSL, that's the viscosity times the velocity over the pressure times the length scale. And then I can multiply and divide. So that gives me QS of L, and that kicks out a 1 over epsilon. But this, I've argued, is order 1. So I can infer that QLS is order of 1 over epsilon. I can then also say then that RLS, by this same computation, is order epsilon. So when we go back, let's see, did I put it on this slide? This is going to be a 1 over epsilon for the solid equation, and this is going to be order epsilon. So we'll we're beginning to see the appearance of the scale separations in the PDE model. Now, the other thing is that the densities of the two materials is quite comparable between melt and matrix. So that tells us that this ratio of pressure gradients to buoyancy forces for the solid and the fluid, they're both about the same in their order epsilon. Okay. So I stuff these parameters in, I drop the tildes, and there's my matrix equation. So there's my epsilon. The dominant forces in the matrix are going to be viscous forces. The next order forces are going to be the pressure gradient. The pressure gradient is going to relate the force on the fluid to the force on the matrix via surface stresses. So that's how those two will couple. And then we have buoyancy forces at lower order. So the melt equation and the boundary conditions. So this is where it gets interesting, and this is where I'm sure someone will complain. There's my dimensionless melt equation. We've argued that this guy should be order epsilon. Should be order epsilon because the only difference between this parameter for the fluid and the corresponding parameter for the solid is the densities, and the densities are quite close. If I expand this out, the QLF dimensionless number, I can re-express it as, and I've made it, I think I skipped this slide. I'm going to make an assumption, and this relates to my comment that the two materials communicate through the pressure gradients, that the ratio of the pressures PF/PS, those are order 1. So what's left here, this we've argued is order 1 over epsilon. So it's 1 over epsilon times the ratio of the viscosities times the ratio of the velocities. And that's going to be order epsilon 2, something we have to go to the data tables for. So these are the numbers that I've got. And this is where there may be some controversy. So if I look at epsilon as my length scale, and I've gone from 1 to 10 millimeters, obviously when we talked about some of the laboratory experiments, this L should probably be closer to the micrometer, or maybe tens of micrometers. And then a macroscopic length scale, and what I'm thinking about here is not the whole Earth, but just a reasonable characteristic length scale that you would see at the macro scale of, say, 1 meter to 10 kilometers. So you get quite a range of epsilon here. There's the velocity range. Now, this is better constrained. Of that the fluid velocity is 1 to 10 meters a year, and the solid velocity might be 1 to 10 centimeters a year. So that's a relatively small order in comparison to this. And now the viscosity ratios, we've got a lot of uncertainty. So when I put these in, I have something that is small, but with many orders of magnitude uncertainty in it. Any comments on this? Or on my choice of numbers? Okay.
I have a question.
Yes.
Is it, of course, the magnitudes matter, but doesn't the scaling also matter? So, as epsilon goes to 0, then, how do these things depend on?
Well, that's the thing. Is that I'm not letting epsilon go to 0. You're never letting epsilon go. You're never really letting epsilon go to 0. What I want to do is I want to get a separation of scales. And I want to know what the leading order term is. And then I can go back and I can say, okay, I know that but epsilon is going to be small no matter what. But maybe epsilon is, it's a question about if epsilon is 10 to the minus 6 versus 10 to the minus 1, in some sense. And I would say that epsilon we can get away with fairly small epsilon here. I don't know if that answers the question or not.
Yeah.
Yeah.
But you're already, with the fluid velocity, you're already you're already putting constraints on your permeability, right?
I have to put constraints in. If I don't put constraints into this, well, no, I'm not, no, because the permeability is entirely a function of the microstructure.
But if you prescribe a fluid velocity, that implicitly, puts a number on the permeability, because otherwise you wouldn't get the fluid velocity.
Oh,
Yeah, but you can think of that as, constraints from geochemistry or something.
But that puts, it's going to put a constraint when we restore dimensions to the values. So what's going to end up happening is I'm going to end up with an equation. I'm going to conclude I have Darcy's law. So I'm going to have phi times the separation velocity is equal to minus a permeability over viscosity times the pressure gradient. That will be a conclusion of this work. But that's all dimensionless. So I haven't, the lab guys, how do you guys get permeability? You put a head on, so you know what your pressure head is, then you measure the velocity, and you make an inference then about what the permeability is here. Here, the permeability, and this is what I was talking about, it's an emergent property of the material. It comes out as an average of something related to the microstructure, and there's no intrinsic length scale in there. Which is not entirely true. The only intrinsic scalings in there have to do with what the microstructure looks like. But it doesn't depend on this number at all. Now, when we go back and we say, okay, here's our PDE model, what does this predict in terms of the flow rate? Well, then you multiply up by these numbers to get the dimensional numbers. So in that sense, it matters.
And the other question, perhaps related, was the length scale for the grain scale, so the 1 to 10 millimeters, right?
Yeah.
So, but the melt, regardless, the melt geometry has a smaller length scale than this grain scale.
Yeah. Yeah, so this now if I make this smaller, actually the whole argument becomes better, because then this epsilon is actually in a better scaling. So yeah, what would you say is the melt channel? A micron?
Yeah. Or 10 micron, or you have to scale it somehow.
Yeah, when I was doing this, I thought, okay, what's the fundamental length scale? All right, it's the grain size. And of course, this would be a very large grain.
Right.
But going to saying that the real length scale should be the melt channel, that actually just improves this, because this whole thing will be smaller. But again, we have all this uncertainty.
The hidden one is the fact that you've assumed that the system is periodic.
Yes.
On the length scale of little l,
That's
as
right.
I understand it. So what you haven't got, what you haven't captured in these equations, is the notion that actually, long before the Reynolds number becomes important, that there may be a channelization.
That's right.
And that you can't then examine.
No.
This is really when this point that if what you know is the porosity, that is not sufficient to give you a permeability, because it's a question of how it's organized on a scale which is large compared with the grains.
That's right. And we'll see a computational example that really, it exhibits what I think the groundwater people have known forever, which is porosity isn't destiny. Porosity is not permeability by any means. So my observation, which is consistent with everyone else's, is that it's controlled by the throats. Yeah.
That, for us, is a statement about the dihedral angle, essentially.
Yeah.
Because if the equilibrium geometry may not actually have throats at the melt fraction that it's separating, because of the fact that small melt fractions doesn't, and under a dihedral angle of 40 degrees, doesn't have throats.
Yeah.
It has channels along the grain edges.
So, but this is getting into, extending the model, including more physics. What we'll see is that this simple model gets us pretty far. It gets us in terms of matching up with what was historically done. And it gives me hope that adding more physics or altering the physics can correct for that and give us better predictions.
The question which I suppose concerns me is whether the framework that you're doing depends on actually having got the physics right. And therefore, whether you have to go back to the beginning,
Oh, you do.
or whether you can actually say, I'm not sure you do, whether you could actually do things within the framework that you've got, right?
No, but for, I mean, we can talk more about this, and it'll come up again. I think the bulk viscosity issue is not going to be resolved by the Stokes model. I think that's completely wrong. I think
I don't think it depends on climbing, but
Oh, all right.
I'll leave that aside.
Okay, okay.
That's another issue.
So I'll argue that we can actually get fairly interesting results, which is to say we can get the equations that I wanted to get if I take this number to be order epsilon, and V to be order 1. Now, how could we do that? Well, if this guy was 10 to the 6th, or 10 to the minus 6, that's consistent with this value. And 10 to the minus 6 is quite small relative to 10 to the 1 or 10 to the cube. So what I view this as, even though V is not order 1 with respect to powers of 10, I'm interpreting it as order 1 with respect to powers of epsilon. So V is between, I'm thinking about it this way. That's a different V. That this velocity ratio I can interpret as order 1 on the epsilon scale. So we end up with this equation. This, by the way, is exactly the scaling that you need to derive Darcy's law. If you don't have this epsilon here, you're not going to get that Darcy. And this should have been an F for the fluid viscosity. You need that, to get Darcy's law, you need that it's the pressure gradient that dominates at leading order. So there are our scaled equations. There's the significant difference between the two fluids, that this is 1 over epsilon and this is epsilon. Those are reflected again in the continuity of normal stress across the interface. And again, that's why I said, again, they communicate via the pressure. What's going to end up happening is that because of this 1 over epsilon, the matrix is going to appear solid. Its motions are going to appear rigid with respect to the fluid at the grain scale. And all the communication happens through the pressure. So now we get into our expansion. Now, just an apology, because when Greg did his derivations, he did it as dx goes to 1 over epsilon dy plus dx. I'm going the other way. I'm saying that this variable is y, so it's going to be dy goes to dy plus epsilon dx, with x being the slow variable. The true solution here is not periodic in y, but this is what you would solve for with unlimited computing resources. All of these terms in this perturbation expansions are assumed periodic in the second variable. And that's a reflection of the assumption of the periodic microstructure. So these are the expanded equations. So let's follow this through. Okay, so we start out, this was our primitive model for the melt after scaling, the force equation. So we put our expansion in, so the dy becomes a dy plus epsilon dx, or the gradient, and this is a divergence operator. There's our perturbation expansion for the fluid pressure. And then the expansion for the strain rate, so again, just going back to the previous slide, we don't just have this for derivatives and gradients and divergences, we also have this for the strain rate operator. So I'm viewing it in that way, that the strain rate is an operation on the velocity field. So there's our leading order piece, which is the strain rate of the leading order contribution to the fluid velocity. Then at next order, or epsilon squared, we've got the slow operation of the strain rate on the fluid velocity field, plus the fast operation on the fluid velocity at next order.
What happened to the bulk viscosity?
Well, this is the melt and this is the microscale, and there is no bulk viscosity. So I'm starting with this is all the simple model, the primitive model.
So this is just Stokes.
That's right.
Okay.
So I'm going to group the terms and underline them. There's my order epsilon to the 0 term. There's my order epsilon to the 1 term. And then when I expand out the divergence operator, there's the order epsilon to the 0, the order epsilon to the 1. So you can see how these things are pairing off. And they'll continue to pair off at higher order. So the leading order melt equation is really straightforward. It says the gradient of the pressure with respect to the fast variable is 0. What's the solution? Something that's independent of the fast variable. Fluid pressure is you only see it on the macroscopic scale, variations on the macroscopic scale. On the at the grain scale, it's a constant. And of course, this is up to some additive constant, but that's the fluid pressure. The other epsilon 0 equations will show up in the first correction, which will give us Darcy, and we'll come to the melt equations. It's the same game. There's my primitive model for Stokes. I expand my divergence operator, I expand my solid pressure, and I expand my strain rate, where I'm doing expansion of both the strain rate operator and perturbation in the velocity field variable. I'll group these, and I didn't have enough room on the slide, so I just peeled off the first two terms. Because of this 1 over epsilon, this one stands alone with an order epsilon, 1 over epsilon. Epsilon 0 captures the solid pressure plus strain rates from the slow strain rates of the solid pressure at leading order plus a correction. And where did this guy come from? Oh, and because we have the divergence outside and the strain rate inside, we have the other term on the leading order velocity field. And similarly, we have these expansions in incompressibility and in continuity of normalcy. So something else you should notice here. I'm going to treat continuity of the velocity field, and I'm going to pair it with the melt equations. I'm going to treat continuity of normal stress and pair that with the matrix equations. So the leading order matrix force equation is just the divergence of the strain rate is 0. And we have continuity of normal stress is 0 there from this equation. When we expand that out. By the way, I see some of you copying furiously. I'm very happy to share my slides with people. Well, we can do something here, which is, in this, Greg alluded this to, which is the energy method in PDE, which is we're going to multiply by U and integrate by parts. The periodic part of the domain cancels with itself. The part that's on the interface, that's 0. So we're left with the integral of the square of the strain rate has to be 0. And there's a theorem that tells us then that this means that it's actually constant in Y. And that's something called the Korn inequality with a K. But what is the conclusion then? It says that at the microscale, the matrix motion appears to be uniform.
Gideon,
Yes?
you're ignoring the surface energy. Have you
I told you, there's no thermodynamics here.
Oh, surface energy is not
surface
thermodynamic.
energy would enter the force balance on the...
Yeah.
Oh, you mean if you wanted to have
That boundary condition, right?
you mean if you wanted to have effectively a surface tension term? Yeah, you could put that in
You
here.
could just put it in there. It could be constant and then just scales up.
Yeah. I haven't played the game.
You're assuming that this thing is 0, and that's leading you to this...
Well, I'm not assuming it's 0. That's 0 because it's a consequence of the scale separation here. So if we go back,
Okay, now, I mean, I'm happy, but...
if we go back to here, the point is that if you want to include a surface tension type term, you would have had to have put it in to the primitive model here, which you could do. Where is it? Where's my primitive model? Yeah, you'd have to put it in here. That it's the difference in the, that you'd say that the difference in the normal stress values was equal to a surface.
Yes, I know, but so I guess I'm motivated by the fact that you're saying you're heading towards the conclusion that the thing that's wrong is that you have a Newtonian model.
Yeah, but I don't know that the surface tension is going to be what fixes it.
I'm saying, I guess I'm thinking that surface tension is not having a Newtonian model. There will be another modification of this model.
Okay, so when I say Newtonian model, which is, and I suppose this is imprecise, what I mean is that I've got isotropic linear relation between strain rate and stress. I'm not saying boundary conditions I view as something else.
Okay, I'll come back later.
All right. All right, this is one long talk. I got to figure out a logical place to stop this before lunch, so let's see where we get. Okay, so first correction of the melt equation. And this is going to give us Darcy. Now we're at order epsilon to the 1. And these are what survive. So we had, this was everything in my order epsilon to the 1 expression. But then we have the incompressibility condition. So this actually simplifies down to classical Stokes. And there's a mu f here that fell out when I wrote the equation. So we have the equation here for the first correction in terms of, or rather the first correction of the pressure field and the leading order velocity field is equal to the leading order pressure field with plus buoyancy. And it's divergence free at the microscale. At the boundary conditions, from what I've argued previously, it's got to match. And now I'm going to play a trick. I'm going to change variables, which is I'm going to move into the frame of the matrix so that I have a Dirichlet condition on the boundary. And I can do that because this is independent of the microstructure. And that was the conclusion of the previous computation. So all I'm doing is making a change of frame. So now I have I still have a periodic condition on the exterior of the cell. But at the interface, I now have a Dirichlet condition. And a very good reference for this, if people are interested, so Greg gave a lot of good references on homogenization, namely Ben Susan, Leon Papanicolaou, his book with Andy Stewart. But for porous media, the really excellent reference is a book that's edited by Hornung. And we have at least 2 contributors to that book in the audience, Ken and Ralph. And in chapter 1, he takes you through the formal expansion of how to get Darcy from properly scaled Stokes in a periodic medium. So we have this expression, and now we have our associated cell problem. So Greg talked about the cell problem for the elliptic problem. This is going to be our cell problem for the fluid problem. So notice I've gotten rid of the viscosity here, which was dimensionless anyway, but it's not here anymore. And now this is just the unit vector. So it's minus the unit vector in direction I, and it's Dirichlet at the interface, divergence free. This, by the way, is what I was referring to when I said that when we get permeability, all the dimensions are gone. So this is a completely reasonable problem. We can solve that. And then by linearity, we can express W, which is the separation velocity, as a linear combination of the solutions to these. So we break up this into its 3 principal components, or 2 principal components if you're doing it in 2D. And it's minus 1 over mu f, so we restore the viscosity, times Ki, which is the solution to this, times the ith component of the right-hand side. And now we can begin to see how Darcy is going to shape up here. So that was from the last slide. But this still has y dependence. So we solved for VF. And the VF was a linear combination of the KIs. The Ki's are solutions to this equation on the unit cell. They have y dependence. This piece here is constant in y, but it's variable in x, but this has y dependence. So that means this has y dependence. We want a macro equation. So if we take a volume average over the fluid fraction, we get Darcy's law. So this is the volume average of the fluid velocity. This is the volume average of the solid velocity. Because this is independent of the fine scale, I just kick out a phi. And there's my permeability tensor, which is expressed as averages of solutions of the cell problems. And this is why I said the choice of the velocity parameter that affects the scaling, and it's going to affect things when I restore dimensions to the equations. It doesn't play any role in what the permeability is. Only the microstructure determines the permeability. This also alludes to this point that that Dan was making, which is, well, what's the permeability? It's not, it's the solution of these problems. The solution to these problems depend on the microstructure. The microstructure is not uniquely determined by the porosity. So again, if we really want to know what these values are, we have to do numerical experiments or measure things in laboratory. So Wenwu, of course, obviously she's got all the technology needed to really compute these things properly for real media. Okay. So I'll start this, but we're not going to get through all of it. And we'll come back to this after lunch. But the leading order solid velocity is y independent. So this is the order epsilon to the 0 term from the force expansion for the solid velocity. So I had this underlined on a previous slide. Oh, one other comment. The decision to take the volume average makes a lot of sense to do. As Greg talked about this morning, you have this approach when you're doing the systematic scale approach expansion. To enforce the separation of scales, you're applying a solvability condition in terms of Fredholm alternative. Averaging this is exactly applying that solvability condition. And it makes perfect physical sense here, too. By the way, that means, that, of course, the fluid velocity is variable at the fine scale. It has to navigate a microstructure. And it's going to have 0 velocity when it hits the grain. So at the macro scale, it only makes sense to take an average. So coming back to this equation, we've determined that this is y independent. So that's 0 because when we take derivatives in this, it's 0. And we don't, so that's gone, and we're left with these two terms. We have incompressibility, and we have continuity of normal stress.
Wait a minute. I'm now bothered by the bulk viscosity. How can it be incompressible?
If the grains, okay. This is the corrector. So the divergence of y, so when I take divergence of y, I'm taking the divergence in the pore, not in the pore, in the grain itself.
That's it. So I'm happy with that being incompressible. But the large scale one can't be incompressible.
This one?
Yeah.
Oh, it's not. Because what's going to happen is this guy's going to move over to the other side. So it's compression on the fine scale of the correction, which balances the macroscopic dilation and compression of the velocity field.
Where's the bulk viscosity in the top one?
It's not there because we didn't put that into the fine scale model. It's an emergent property. So this equation this is now getting the correction, but this is still starting with the model that's incompressible at the grain scale. Under these, again, these are the models that we'd solve if we had unlimited computing resources. And as we saw in the
I'm bothered because the shear viscosity
yes.
also comes from a grain scale motion of the solid, just like the bulk viscosity does. So I haven't understood why you allow the shear viscosity to come into this, but not the bulk viscosity.
Because-
any separation at any level that I can see between those two viscosities.
So it's a perturbation expansion of a model that's valid at the grain scale. So at the grain scale, we agree that when we really are zooming into the grains themselves, the grains are incompressible, effectively. So now we're doing, so that's our primitive model, and we're doing perturbation expansion on that model. What's going to happen is that as we solve the corrections successively, we'll see that there's this emergent property that plays the role of the bulk viscosity.
But
Let's put it this way. I'm pretending with these velocity fields that I can zoom in and identify this is grain, this is melt.
yes, but the emergence has to also describe the shear viscosity.
Oh, it will.
So I haven't understood why the shear viscosity appears and the bulk viscosity doesn't.
This is
and the
because
microstructure of both of them is the same.
that's the grain scale shear viscosity, not the macro shear viscosity.
Oh. Okay.
Okay.
Yeah.
And it's 12:30, and maybe we'll continue this after lunch. All right, thanks everyone.